Welcome. In this lecture, we will talk about the alternative routes of iron making. And I will give just the brief introduction to the direct reduction as well as the smelting reduction process. Basically, the direct reduction, introduction to direct reduction process I will first cover, and in the next lecture we will cover about the introduction to smelting reduction, and a part of the direct reduction also will continue into the next lecture. Now, this is the thing which I want to cover in this lecture. First of all is the significance of the alternative routes of iron making. That means what is the need of these alternative routes of iron making today. So, that has to be discussed first, and then I will give introduction to the DRI and these processes, then properties and use of DRI on the sponge iron, and then I will go to the introduction to the smelting reduction process. Now, what are the driving force for alternative routes of iron making today? First is the coke-free process. Okay, so alternative routes of iron making should be coke-free. As I said, that is, the coke constitute around more than 50% of the total cost of liquid or hot metal production. And it is due to the fact that we are depleted with the coking coal reserves. Okay, we have very limited coking coal reserves, and that too the coking coal has other problem of high ash content. So, we are dependent on importing the coking coal, and then we make the coking process in India. Actually, we do it, and we mostly dependent on import of the coking coal from Australia, and then of course we blend it with the non-coking coal or other medium coking coal, and then we charge it into the coke oven furnace, and in the form of stamp charging sometimes, as we have discussed already. But still, that is, the coke become very costly. Okay, and as I said, it constitutes around 50% of the total cost of the hot metal production. So that's why. And besides, the coke making process itself is very polluting, and that's why from environmental point of view it is also not good. So, people are looking for a process which can be without the coke and using the non-coking coal that is prevalent in India in a large amount. Okay, so this is the first. Second is the environmental friendly process. As I said, blast furnace has ancillaries like this coke oven plant and then sinter plant also. Those are polluting, both are the polluting plants. So, we have to look for in routes or iron making that is coke free, as well as where you do not require the sinter. You can directly use the fines. Okay, so such that these units like coke making units, sinter making units, if we can get rid of this, and we can produce in a very simple system, we can produce the iron. Okay. Then recycling of the waste, because in the steel plant we generate lot of waste. For example, in the steel plant we produce the EF dust, it is iron bearing dust, and then your blast furnace also, blast furnace dust, all are iron bearing dust that is just is wasted, as well as the slime produced during the iron ore beneficiation contains lot amount of iron. So, all this solid waste has to be utilized, because today's practice should be the zero waste process. Okay. So, recycling of the waste. So, you know that we cannot use it into the blast furnace, because in the blast furnace is a very complicated chemical reactor. It is highly efficient, both, as I repeatedly am telling, it is thermally and chemically highly efficient reactor, but it requires, for to maintain its good efficiency, it requires very good quality of iron, there is the blast furnace burden. Okay, so burden quality has to be very good in the blast furnace, otherwise it is a very complicated and very efficient reactor, because the quality of the burden has to be good because of its complexity, because you have a dry zone, and then you have a wet zone in the bottom of the blast furnace, and then it is demarcated by a cohesive zone, and they interact in such nice way, and finally we get the product, hot metal. So for this interaction of the dry and wet and the cohesive zone in between, we need a very good quality of iron ore burden that maintains a very good permeability into the blast furnace such that the counter current gas solid liquid flow is not hampered. It goes very smooth, because in this case the gas interacts, gas is coming from the bottom and interacting with the liquid and then the solid, and so this is the counter current liquid gas then gas solid reactor. So it requires a tremendous permeability for the gas to pass through, and that can be ensured by a very good quality of raw material. And so in the blast furnace we cannot compromise with the raw material. That's why we have to use coke in place of the coal. Coal we cannot directly charge in the blast furnace. We have to place a coke, and coke is made from a very special grade of coal that is called the coking coal. Okay, so that's why. And then the iron ore, and also the ore is charged in the form of sinter and pellets mostly, and lumpy ore very rarely used, and it is now nowadays limited to 10 to 20%. So mostly it is sinter, or sometimes it is pellets are also charged. Pellets are a little costly, and but still it is most of the blast furnace operate with 80% of sinters. So that means that is the iron ore has to be agglomerated into better burden. So waste utilization remains a distant thought into the blast furnace. It's quite difficult to use this waste, and unless these waste are converted to a agglomerate product and with a sufficient strength and reactivity and all these things. So that requires a lot of, so we have to find some process where this waste can be recycled in a less, in very cheaply or in a less costly way. Okay, so recycling of the solid waste. So we have to find out some process where we can use this solid waste in an economic way, right? So this is, and then utilization of fines. As I said, we generate a lot of fines during mechanized mining also. Around 50% of iron ore mines in the form of fines. So this fines has to be utilized. Besides, we have blue dust, a rich iron ore blue dust, and those has to be fined, and they do not take place, they do not find a place into the blast furnace directly unless you pelletize them, and pelletize is a very costly process, as I said, or that is the fines you can sinter them and then use it. Okay, so sintering, that is also cost involved. So that those are the things. So utilization of these fines, if those can be directly used in a process where we can directly use it, or we can use it in a very economic way. So utilization of fines. So these fines has to find a path. That's why there's alternative routes of iron making. Then the scrap substitutes. Basically, the scrap is depleting day by day because of technological development, continuous casting technology development. There's the in-house scrap generation has decreased. In-house means in steel plant itself, the scrap generation has decreased because of this technological development. Because ingot casting used to produce a lot of scrap, but with continuous casting, scrap has decreased. Besides, the process advancement has been there that doesn't generate too much of scrap. So the scrap is depleting day by day. So we have to substitute the scraps by some other forms of solid metallics. Okay, so that is also another way or another driving force for the alternative routes of iron making. So these are some of the driving force for alternative routes of iron making. Okay, so now let us see the various methods of iron making. And we know there is a iron making process, conventional iron making process is the blast furnace or the mini blast furnace. MBF represents the, here MBF represents the mini blast furnace, and mini blast furnace are similar to the blast furnace. Only thing is that here the shaft height is less, much less compared to that of the blast furnace, because as we know there is the quality of burden is required to be very high because of very long shaft, and during the descent of this raw material, okay, they can generate fines and block the pores, choke the shaft. That's why the quality of the burden material becomes more and more important as the shaft height increases. If I decrease the shaft height, then I can compromise to some extent with the quality of the burden. That's why the mini blast furnace came, where you can charge more of lumpy ore, little that is the low quality raw material also you can use in the MBF. So that's why MBF come for the, especially for the small production, you can use the mini blast furnace. For example, Tata Metallurgical has a mini blast furnace, Tata Metallurgical in Kharagpur. So there are several places where, or you can, if you use the charcoal as a reductant in place of the coke, then also you have to go for the mini blast furnace, because you cannot use the charcoal in the blast furnace because the charcoal doesn't have sufficient strength. Okay, so the charcoal blast furnace, mini blast furnace, and the conventional blast furnace are the conventional. These are the process I am talking about, and in this case the reductant are mostly the coal and the coke. Coal is there. Sometimes coal means there is in the form of pulverized coal injection you can use. You can use the charcoal also for mini blast furnace or charcoal blast furnace. So these are the reductant, and oxide feeds are basically the lumpy ore, sinter, and the pellets. This is and what is the product? You get a hot metal, and which is saturated with the carbon, and it has also impurities like silicon, manganese, phosphorus, sulfur, like this. Okay, this is a conventional method. Okay, the process are blast furnace, mini blast furnace, charcoal blast furnace, like this, and these are basically you get a hot metal out of it. Now there are other two methods that I am going to come, that is, one is called the direct reduction process and another is called the smelting reduction process. So second one is the direct reduction process. What is the direct reduction process? I have just introduced the DR, gas based DR, coal based and gas based DR. DR represents the direct reduction process. This is one of the alternative routes of iron making process. Here basically the iron ore is converted to iron in a solid state. Okay, that is called that, and it can be, the reductant can be coal, non-coking coal directly, or you can use a reformed natural gas, and that is also today called the direct reduction process. Because coal based process, basically direct reduction name derives from the fact that is you are reducing the iron ore in presence of carbon at high temperature, where carbon directly participates into the reaction. That is the definition of direct reduction, and this process, that's why I call the direct reduction process, because you can reduce the iron ore in presence of coal directly at high temperature. Okay, at more than 1000 degrees centigrade you can do that thing. That is called the coal based DR process, and you can basically in this coal based DR process, there is a reductant gas CO is generated by in situ generation of CO. So CO is generated in situ because of carbon gasification. So because of iron ore reduction, whatever the CO2 is generated, that gasifies the carbon, forming the CO gas. That CO directly reduce the iron ore, and since carbon is directly participating into this reaction through the carbon gasification reaction, this reaction is called the direct reduction. We have talked about that thing. Okay, but you can reduce the iron ore by reformed natural gas. You can take the natural gas, you reform it to CO and H2, and then you can put that gas to the shaft furnace to reduce it. Okay, so that is called the gas based DR process, and this is the coal based. And here what you guess, what are the reductant? Coal, non-coking coal for the coal based DR process, and natural gas for the gas based DR process. And here the oxide feed is lumpy ore or the pellets. This is the two, because it is a shaft furnace, usually lump ore and pellets can be used. And the product is called the direct reduced iron. The product of direct reduction process is called the direct reduced iron, and or the sponge iron. You can call it sponge iron. Okay. Why it is called sponge iron? It is not like spongy like things, but if you see the metallograph, a microscopic view of the sponge iron, you find a lot of pores and it appears like a sponge. I will talk about that thing. Okay. And then another process is the smelting reduction process. There is the smelting reduction process. Here what you do, you first melt the iron ore itself, iron ore, and first melt the iron ore by generating an intense heat by burning coal in presence of oxygen. Most of the cases it is the pure oxygen at room temperature is used, and it burned with the coal and forming intense heat, and in that heat you can melt everything. So you melt the iron ore also, and then in the liquid state you can reduce it. That was the definition of the smelting reduction process, but nowadays you do in a two-stage process also. I'll just come. So in single stage, what you do, you melt everything. That is the idea of smelting reduction. Why? Because the blast furnace is a complicated reactor. As I said, you have a dry zone, and then cohesive, and then the liquid zone. You have to maintain this. You have to correlate these three zones so nicely such that the whole reactor operates very smoothly. Otherwise, lot of irregularities like channeling and then flooding that take place in the blast furnace. You are not cautious about the operating parameter and the burden material. So these factors makes the blast furnace very vulnerable. Okay, so that's why the smelting reduction process, and since we are looking for a low grade burden material like non-coking coal and low grade iron ore, all these things. So that's why I thought that is the blast, this type of reactor will not be suitable. We have to find a reactor where this type of irregularities like channeling and then flooding and all these things as blast furnace is operated with are not encountered with. Okay, so that's why the smelting reduction furnace can, there everything you make it liquid. So everything is liquid in the reactor, and then in the liquid state you reduce the iron ore and produce the liquid iron. So that was the idea, and then the slag metal separation, you can tap out the hot metal. That was the simple idea, and you can use any kind of raw material irrespective of quality of raw material. You have to bother about that thing. And secondly, and that was the single stage smelting reduction SR process, and then there came some other process like blast furnace, that is the two-stage process. It is similar to the blast furnace, but the dry zone and the wet zone are completely separated. Unlike in the blast furnace, what in the blast furnace they are connected. So the problem comes. So here you separate out the dry zone and separate out the liquid zone, and you control them independently. Okay, so that is another process, the smelting reduction process called the two-stage process, and that is most popular. So in SR method, that's why I told, that is the last two routes, that is this and this. So you can find in the SR method, what you can find, that is the reductant used is basically the coal and the oxygen. Most of the cases pure oxygen you use it, and in some cases you use the preheated oxygen and DGR blast also. And the iron ore feed, you can see the feed, lumpy ore, fines, pellets and waste. This is very important. Any kind of waste also you can utilize it. Okay. And the product is liquid hot metal, just similar to the blast furnace. So you are producing a hot metal by using non-coking coal. It is the non-coking coal you can use it. Okay, so only the reactor is different, totally different reactor. So you can use the non-coking coal and you are using pure oxygen anyway. So a non-coking coal and the waste, that is the any kind of waste, fines, pellets, lumpy ore. So anything you can use it. So we have just removed all types of restriction about the raw material, and we are very flexible with the raw material. That is the advantage, and that's why what you have to do, basically we have to change the reactor. So we have changed the reactor, and then we can produce a hot metal of similar quality that of the blast furnace. That is the beauty of this process. In SR method, hot metal of the blast furnace quality is obtained without using coke, where reduction and smelting are separated and carried out in two separate reactors. Okay, I think this is, you understand about the difference. Now we talk about the introduction to the DR and its processes, that is direct reduction. What do you mean? Little depth I am talking about here. What is called a direct reduction? Direct reduction includes a family of processes in which iron ore in the form of fines, lumpy ore and the pellets are converted into the solid state iron. Okay, either by using solid or the gaseous reductant. So you can see the source, the iron ore, you can use the fines directly, you can use. Now it is the reactor, solid state. Basically you are reducing the iron ore in the solid state to produce the iron. And what is the raw material? You can directly use the fines. So, reactor will be different. You can use the lumpure, you can use the pellets also, and you can use either the solid reductant like non-coking coal, or you can use the gaseous reductant like reformed natural gas. So, this is whole family of this process is called the direct reduction process. So, as I said, non-coking coal, reformed natural gas are used as reductant. Instead of coking coal, you can directly use the non-coking coal, and you can in solid state you can produce the metallized iron. And this non-coking coal and reformed natural gas, they are basically the source of energy also. There is no other energy source. This the non-coking coal is the source of energy, as well as it acts as a reductant. Similarly, natural gas acts as a source of energy, as well as reformed natural gas act as an reductant. Okay. And you can burn some amount of the natural gas basically to produce the energy to sustain the process. Okay. So, this is the thing, and final product of DR process is solid iron. That is, as I said, you are solid state, we are reducing it and it is a solid iron. So, finally, a task that is remaining is to melt it. So, there also it also involves some energy that you have to do, that limitation is there. So, from direct reduction process, the product is a solid iron. So, you have to melt it, that you have to keep in mind. So, as a result, it requires some more energy next step that you have to think about. Okay. What are the products of this DR process? Is the hot DRI. When you are reducing it, you are getting the hot DRI. In hot condition, if you have a provision, you can directly charge into the electric arc furnace. Then basically what happens, you can save a lot of energy. Or in the high temp process, you can, if you have some provision of channeling the hot DRI directly to a EF in a distance place, that is also possible. That is also called the high temp process. And or what you can do, you can cool this DRI and store it, and then transport it or you sell it to other places where they want to use it. Okay. So, that is called the cold DRI. Cold DRI, what is that? Hot DRI, and then you cool it, because you do not have provision for charging it to electric arc furnace directly. So, then you have to cool it, because high temperature you cannot keep the DRI and it will be very prone to reoxidation. So, what you have to do, you have to cool it by inert gas or something. You have to, inert atmosphere, you have to cool it to room temperature, and you can store it, because room temperature you can store it for a long time, because its propensity for reoxidation is less at room temperature, and also you can passivate the DRI before you cool it. So, that is called the cold DRI, and then you use it whenever required. That is why its product is hot DRI, cold DRI, and HBI, hot briquetted iron. Hot briquetted iron, what you do here, basically the hot DRI is briquetted, and what is in a bigger shape. And if you do the hot briquetting, what is there, basically you are decreasing the surface area. So, its propensity for deoxidation will decrease to some extent, because you are reducing the surface area, because the DRI is very porous. Okay. So, if you briquetize it, you to some extent you can, on the surface you can reduce some amount of pores, and also you increase the surface area. So, when you briquetize it, its propensity for deoxidation decreases to some extent, and you briquetize, and then you can, besides the briquettes also, sometimes its melting efficiency is also better anyway. So, this is the three product, one is the hot DRI, another is the cold DRI, and the hot briquetted iron. And what are the reactor you use for coal based DR process? Mostly the reactor that is used is called the rotary kiln. What is that? It is basically cylindrical reactor, and it is inclined with the horizontal such that the material can move under gravity, okay, and under a rotating condition it moves under the gravity. So, some inclination is required, and cylindrical reactor, simple like that, and you burn the coal from the exit, you just give the air and coal and you burn it. Coal burner is there, it generate the heat, and you give some carbon is also used as a reductant. So, carbon generate the in situ CO and it reduce the iron ore. by taking the heat from the furnace atmosphere. Okay, so this is the process basically in case of the rotary kiln. Okay. And for gas based process, you have different reactors. One is the fluidized bed reactor, where basically you can directly use the fines and you can use the gaseous coal, there is the CO gas after coal gasification, or you can use deformed natural gas from the bottom, and the fines can be fluidized and can be reduced. Okay, this is called the fluidized bed. Or you can pelletize, okay, or you can pelletize the ore, okay, and use it into the shaft furnace, or you can use the lumpy ore also you can use in a shaft furnace. Shaft furnace, you know, it is also a cylindrical reactor, and it is a counter current gas solid cylindrical reactor. From the bottom the gas goes and the solid comes from the top, and it is a continuous reactor, shaft furnace. So you can use a shaft furnace, or you can use retort. Retort is basically you have a reactor, cylindrical reactor, and it is heated, externally heated from the sides, such that the heat penetrates and the material inside get reduced. If you have reductant inside, it will automatically get reduced. So there is no gas flow, basically retort. So externally heated from the side, and heat penetrates in the radial direction from the surface towards the center, and then the material get reduced. So that is like this tunnel kiln is there, that is the type kind of retort, and fluidized bed reactor is there, and shaft furnace is there. Most of the modern DR process like Midrex, HYL, all are the shaft furnace based process, and some fluidized based process are also there in place. And retort process is basically the tunnel kiln. In the tunnel kiln, basically in a retort, the material is kept cylindrical retort, and it is heated from the side. Okay. And lot of retorts are there, and then these retorts move through the tunnel where the heating arrangement is there by the burners. Okay, and heat penetrates through the retort from the surface and the material get reduced and you take out. So it is a number of retorts are there arranged in the car, and that car moves. And the total global production is around 100 million ton DRI production, out of which India produces around 30 million ton, maybe 28 to 30 million tons, and it is still now today is the leading producer of DRI. So now what are the reaction involved into the DR process, the gas based process? Reforming of the natural gas. First you reform the natural gas. You can reform is using CO2, for example CO2 plus, there is the CH4 with the CO2, you can reform, and then you can get CO and H2. It is called the CO2 reforming. Basically the idea has come, that is from the waste, that is the off gas from the reduction shaft, you can directly use for the reforming process for CO2 reforming. Or you can steam reforming, you can reform the natural gas using steam. So, and then you can produce the CO and H2, and all this reforming process is endothermic used to supply the heat. Though this is called the steam reforming. Okay. Basically you are oxidizing the methane to CO and H2, and think is that what is the source of oxygen. You can use CO2 as a source of oxygen, and it is, and then or you can use steam, simple steam as a source of oxygen. Favorable conditions are there. For first example, for all this reforming process you need a catalyst, otherwise the process is not very fast. So nickel, presence of nickel catalyst make this process very fast, and also temperature comparatively higher, greater than 700 degrees centigrade, and you have to use a low pressure. Obviously you can find in this reaction the moles produced is 4 moles of 4 gaseous moles of produced out of 1 gaseous reactant, 1 mole of gaseous reactant. So the pressure will increase. So at low pressure obviously this reaction will move in the forward direction, and the reduction is basically Fe2O3 to hydrogen forming Fe and H2O. Okay, and also it can be reduced by CO. So this is the overall reaction. And in case of the coal based process, what is there, your reductant gas is basically generated by carbon gasification reaction. You are well known with it. So, is the carbon can be gasified by CO2 to CO, and this CO can be used for the reduction of Fe2O3 to iron in three sequential steps, like Fe2O3 hematite to magnetite, magnetite to woostite, woostite to iron. The similar in the gaseous reduction also, but I am not giving the step only, these 3 steps also applicable here. But in case of the coal based process, main thing is that we are generating the in situ CO by gasifying the carbon inside the reactor itself. So, the coal based reactor acts as both as a carbon gasifier as well as reduction unit, both. So, this process, as you know, this is a highly endothermic and requires around 1000 degrees centigrade for appreciable production of CO. So, this process basically takes place around 1000 degrees centigrade. Basically, higher temperature is preferable, but thing is that from another point of therefore, because of sticking and agglomeration formation, we do not go to very high temperature. Usually, this process is carried out around 1050 degrees centigrade. I'll come to that thing in details. But that's why the coal based process is little high temperature process compared to the gas based process. Gas based process can be operated within 900 degrees centigrade, but coal based process, it has to be around 1050 degrees centigrade. Okay, I will continue this lecture in my next lecture. I am closing this, and I will continue in the next lecture the direct reduction process as well as the smelting reduction process, the introduction. Okay, so thank you.